Welcome to the 14th tutorial. I think I got it right this time. I believe this is number 14 after 13 part 2. Just like what I said earlier, the two-parter is what fixes it. Because I've always been one behind. Now because there were 2 parts, I'm actually caught up. So we are still on the moon, on the in the DeltaGlider. We're on the pad here at Brighton Beach, and we're going to fly back to the Earth. So is flying to the Earth as hard as getting to the moon? No, not even close. Trying to land on the moon is akin to throwing a dart onto a dartboard from quite a distance and trying to hit the bullseye. I would say that trying to get back from the moon to Earth is about as easy as throwing a magnet on the fridge. It's that easy. I mean, the moon is a small target. The Earth is a huge target. It's a huge gravity well. It's ready to take you down, but all you have to do is just get the direction right. If you get the direction wrong, you'll be on your way to interplanetary space. I kid you not. If you get the direction wrong, you burn in the opposite direction, you will probably end up in a near-Earth orbit around the sun. So just keep that in mind. So now two notes about refueling. If you have auto refuel enabled, you will refuel as soon as you touch the pad, instantly. That's done from the launch pad. If you go down to the second window parameters, and I believe it's the 4th checkbox down, auto refuel on pad. I don't check that because I don't like my ship instantly tripling in mass as soon as I touch the pavement. I prefer to refuel manually, and I will walk you through doing that, although you won't be able to see it happening. Okay, so if I scroll down, you can see we're basically almost out of fuel, so we are going to have to refuel. So what we're going to do is we're going to press F4 to get the menu, and you will have to have the scenario editor enabled from the modules tab. This is a little bit of a cheat, but as long as you do it in the right places, it's okay. So go to function, and you go to scenario editor, click OK. You'll see GL01S. Highlight that and click edit. And now what you want to do is under the section MISC, you press propellant. And it's not tank 1 because that's full. 390.5, yeah, it's tank 2. So what you're going to do is you'll see a window with a black bar, and you're going to drag that bar all the way to full, and look at that. We've just refueled. Just click done, done, close, press F4, and magic, like nothing even happened. So we have a completely full DeltaGlider again, and we'll be using hardly any fuel for this. In fact, you know what? Well, in some craft it matters what your maximum landing weight is, and because relatively speaking, Moon to Earth does not use, as long as you fly it right, does not use a lot of propellant. You might need to set the, you might need to not refuel all the way. If we were coming back in the DeltaGlider 4, we would absolutely not refuel all the way. If you do, we'd have to do a fuel dump, which is entirely wasteful and completely destroys the purpose for doing Delta V buttons and takes all the fun out of it. Okay, so I'm going to come out of here because it's kind of annoying. So going back is extremely easy. We need to know 2 things. When we get into a low orbit around the moon, we will need to know exactly how much delta V to expend. And guess what that value is? If you go back to the spreadsheet that we made in 13 part 1 at the very end of the video, if you open the mission manual, or you don't have a copy. If you if you pause the video where I'm looking at the mission manual, and I'm talking about the orbit entry delta V in the section F62, that will tell you the amount of delta V that we need to enter the lunar orbit from the translunar trajectory. And as it turns out, a rough approximation would be to reverse that delta V in the opposite direction. And it works. So it's 815 meters per second. That's what we're going to use as a preliminary burn. The only thing you have to do is do it at the right moment. And I can tell you exactly where you need to do that by getting into a low lunar orbit. Basically, what we need to do is we need to figure out what the time to burn is. And we can't do that because we don't know precisely the amount of delta V that it's going to take to get out. Now, unlike the Earth, where we just have to say, oh, it's about 9,600 meters per second, depending on how you fly the flight. No, that's not the case here. If you fly the flight perfectly, and I mean perfectly, you turn the thrust on precisely when you say you're going to turn it on, you turn it off precisely when you say you're going to turn it off, you can estimate the delta V that's going to be required to within 10 meters per second because there's no atmosphere. There's no drag. Every force is conservative. So you're getting every bang for your buck. Now, to avoid math, I'm not going to do it. Okay. So let's start setting up. We're going to get into lunar orbit. I prefer my green HUD on the moon because we're still in a vacuum. So what we're going to do is we're going to achieve orbit. So we want the frame set to equator. And we're going to change the radius to altitude because we're concerned about altitude. And I'm going to put this one on VOR VTOL. And make sure that this is configured for nav2, which is the pad. Okay? And then go over to surface here so that we can monitor what's going on. So we're facing south right now. Remember, we like retrograde orbits because retrograde is the free return trajectory. So it's a good idea to get in the habit of going into a retrograde orbit. So that's exactly what we're going to do. So we're going to take off, we're going to turn right to 270 degrees, and then we're going to accelerate. Now, unlike the Earth, we're going straight up. So what do we need to do? We need to turn RCS on.
Rotation.
Okay. Elevator trim does not apply here. So what we're going to do now is turn on horizon level, and then we're going to begin adding hover thrust. Although, before we do that, probably a good idea to turn our lights on. And again, make sure that the hatches and airlocks are closed. We're not connected in with anything, so even if they were open, we wouldn't really be experiencing anything out of the norm. And that's about it. Horizon level is on, and you can see it's working because it's actually forcing us up. You can actually see the jets firing right here. They are firing to keep the nose wheel a little bit off the ground, which means we're using fuel. So we need to get off the ground. We begin by adding hover thrust. We're way lighter on the pad now. Keep adding it a little. Okay, that's it. We've just come off the ground. Just give it enough so that you come off the ground. And now you give yourself RCS rotation. We're going to turn 90 degrees to 270, right? And the less hover thrust you use, the better. So don't try and go very fast. It's not very helpful. So now we're approaching 270 degrees. We're going to begin adding some left yaw. And when we get to 270, and right there, that is it. Okay, and once we are sure that we have cleared the horizon, we can start adding thrust. And it's unfortunately, it's very difficult to tell because that's all the lighting we have. We can put your gear up now. We're above 500 meters.
Radiator retracted.
Yeah, So I think I see a hill in front of us. So in this case, we're going to have to add just a little bit more hover thrust. We're going to pick up a little bit of vertical speed, maybe about 100 meters per second vertical speed, until we get over that hill. And I can barely see it, but basically what I'm looking at is stars being blocked out by the lunar surface. Because I have a crystal display monitor, so it's realistic brightness. I actually can't see the lunar surface right now. It looks like we're coming over just about now. All right, I think we've got it. So go ahead and lower your hover thrust until you're in a hover. Right about there. That's good. Well, we're not in a complete hover. We're in an ascending hover. And hit your main engines until we've got an orbit. 3, 2, 1, now. And now we are moving away from the pad in pursuit of achieving orbit. Okay, here comes our prograde velocity vector. All you have to do is keep that off of the lunar surface. So I'm going to begin reducing hover thrust now because we don't need as much now. We need about 1700 meters per second to get into lunar orbit. Why does my this thing looks a little bit wonky? I don't like that. There we go. I forgot to change it to ship. Okay, looks good. So the faster you go, the less hover thrust you need. I've got hardly any hover thrust going now, just over about halfway to orbit. And again, you're just looking at that eccentricity value to go to 0. Although you do need an apoapsis altitude of at least 24 kilometers so you don't slam into the surface. So right about now, we're going over that very high hill that I was concerned about hitting. Pretty soon that will probably soon to eclipse the base. We're above 1,000 meters per second now. Probably have enough now to cut hover thrust completely, but just keep an eye on that. Make sure it doesn't go below the horizon. So now we're on specifically main engines. We're essentially a golf ball that's been cast forward at maximum speed. And just now we have a very nice orbit taking shape. And this is about as low as you can safely orbit the moon. Okay, I see we are over the mountain now. I see stars below the horizon, so that means we have safely cleared the hill. Almost there. And yeah, I can't see the base, so that must have been a pretty high hill. Okay, 1,600 meters per second, getting ready for cutoff. Okay, I'm reducing thrust now. And we've got 27 kilometers. But we want to go a little bit higher. We're going to go actually up to about 100 kilometers because that's where the Viz-FIFA equation was done. And if we choose 100 kilometers, we won't have to redo the math. So right there, main engine cutoff. We're in orbit around the moon, and even our periapsis is above the surface of the moon, so we are good for one orbit around the moon. We won't even have to circularize. That is it. Hover thrust is off. Main thrust is off. Go ahead and disable your hover or your horizon level autopilot. Change your HUD to be orbit. And activate your prograde autopilot. And if I look outside, that's right, we're in lunar night, so you can't see that the radiator is deployed. Now that we're off the ground and in orbit, we can turn our docking lights off because that's just lighting up space for absolutely no reason, irritating people like myself who came to the moon for the sole purpose of being able to actually sleep at night. If I had a choice of where I could sleep, I would say the far side of the moon when it's dark, because there ain't no artificial lights that are reaching the far side of the moon. The only light that reaches the far side of the moon is starlight, planetary light, zodiacal light, and when it's in sunlight, the sun. So when you're low, about 7 kilometers, just keep an eye. This is very similar to Flight Simulator. Keep an eye on where you can see stars and where you can't. Right now, I see them blotting out at about 355 degrees. You're okay as long as it doesn't cross the prograde velocity vector. If you see stars blotted out on your prograde velocity vector, that's probably a good indicator that you're about to crash into a mountain. And yes, that happens. You have to be very careful around the moons of Jupiter, because they orbit very fast around Jupiter. It's not like the moon, which orbits the Earth very slowly, and you can get yourself into a lot of trouble by realizing, oh no, I'm going 10 kilometers per second and I can't stop in time or change the trajectory because Jupiter's huge. And then you wait about 5 minutes before you inevitably smack into the surface at about 2 kilometers per second. Okay, so that's it. We're done until we get out to our apoapsis, where we will circularize for the sake of making sure our equations are just about accurate. So see you at apocylene? I think that's what it is. Okay, so I stopped a little bit early, as I normally do. I changed the right MFD from surface because we don't need it anymore. It's really irrelevant to map, and realized that we'll be seeing Lunar Dawn, so I decided to stop the video and give us a chance to see Lunar Dawn, because it's nothing like the moon, or nothing like the Earth. It's very strange. It's 100% shadows. There's no diffraction, which means you're going to see the sun when you come around the planet. The sunlight will not get bent up by the atmosphere, and there won't be any yellow, orange, or red diffraction. It'll just be straight light from the sun and any reflection on the surface of the moon. So we should be getting the limb of the moon just about any second now. And there will be no warning. It's just you'll suddenly see parts of the sun. Which is probably one of the first things that I would complain about if I were an astronaut, would be the sudden sunrise. Just say no fair. It didn't give me any warning that it's coming up. Isn't that just the coolest thing ever? It just magically appears. Onward to apocylene. It really is a little bit unfortunate that the moon is airless, because I see those craters and I just want to dive for a canyon run. But unlike the unlike the X-Wing fighter, these space planes can't act like airplanes in the presence of vacuum. The reaction control system just doesn't have enough energy to be able to maneuver in that sort of way. So we're going to use hardly any propulsion to achieve the orbit that we need. We're just going to run the engines on about 5% for probably about 4 or 5 seconds, and that will be all we need to circularize here. Okay, that's really circular. So now it's time to plan the trip back to the Earth. So I mentioned this direction. So how do we get the direction right? Well, you got to remember which way the moon orbits. The moon orbits the Earth in the same direction that day and night is. So it's prograde. We're orbiting the moon retrograde, which means if the moon is on our right side, if the Earth is on our right side, it means that we're going against the velocity vector. If it's on our left side, it means we're going with the velocity vector. And that is the important thing to get right. So I'm going to look around for the Earth just a little bit and see if it's here. And I don't think it will be, because Brighton Beach is on the near side, and I believe we're on the far side of the moon. Yeah, a quick check of longitude. We won't be able to see the Earth for another 40 degrees. So instead of trying to look for it, we're just going to cut to the chase here. If I change the reference to Earth, now you'll see this is our current Earth orbit. And that gives you an idea of when you should and shouldn't burn. You burn when that orbit... You burn when you're at the apoapsis of that orbit. If you burn when you're at the periapsis of that orbit, you're in trouble. That basically is going to allow you to break free of Earth. So if we do HUD now, that's our current orbit around the Earth. And if you notice, we're actually pretty close to the prograde velocity vector, which is demonstrated by how close this current line representing where we are is compared with perigee. Yeah, that's the prograde velocity vector of the Earth. So if I disable prograde right now and just wait a few seconds, you'll see that if we were to hit the engines now, we'd be hitting them in the prograde velocity vector with respect to the Earth. So what that means is the speed that the moon is going around the Earth plus a little bit of extra speed will allow us to break free of the Earth. Because look at how scary that orbit is getting. And now you can see we're basically... oh, well, there it goes. Okay, so with respect to the Earth, we're unbound to it, but we're bound to the moon. So if you were to hit your engines right now, what would actually happen is you would just widen that open trajectory. We're bound to the moon, but we're escaping the Earth. So if you escape the moon while you're escaping the Earth, the result is going to be you orbit the sun. So do not make this mistake. You want to burn when your prograde velocity vector of the moon lines up with the retrograde velocity vector of the Earth, which I can't view right now. And that will get you home safe. So what we have to do now is figure out where precisely in the orbit this prograde velocity vector is for the Earth. And if we don't use math, our only choice is to use the HUD and see when we swing around to it, and note our longitude at that time. So this number is good for only about a day, because the moon is moving around the Earth So the longitude of that prograde velocity vector will change as the moon itself orbits the Earth. In the span of a 2-hour lunar orbit, this isn't a problem. 10 lunar orbits, probably still not a problem, but you're losing more efficiency. 2 days later, yeah, it's a problem, because then you're not going to be heading towards the Earth. You're going to be heading a little high, which means you'd underburn and you'd waste fuel. So what we're going to do now is we're going to warp time forwards, and we're going to need to flip back and forth to our orientation on the Earth versus the moon, and keep a good idea of where that is. Now, you can cheat a little bit by turning on the cheat codes, and you find out that this is, let's see, I don't know, looks like Auriga is the constellation. That's the constellation that the prograde velocity vector of the Earth is in. So we're just going to keep swinging around to that point. Okay, so we're about as close as we're going to get now. And the way I can tell is if you look at this PET, when that starts counting down to 0, we're at the periapsis. If we wanted to escape the Earth-Moon system and go off into the solar system with a little bit of an inclination, this is where we would do it, right here. Because if you look, even though we're tilted a little bit, if you look with respect to the Earth, we're actually lined up with the prograde velocity vector. What's going on is we've got a little bit of plane change going on. So, moving from the Earth, wow, that is a beautiful Montes. Look at that. If you burned from this location we're in now, you would be having an issue with trying to, that's not absolute direction. That is incredible, seeing those mountains lift up off of the Maria there. Okay, so this is the exact opposite location you would want to be performing this burn. So I'm going to write this down on B66 of my list. We'll go to auto-reference the moon, and if I look, our true longitude is about 201.6, the TRA, or sorry, TRL. And what that's going to do is that refers to specifically where we are in the orbit. So what we're going to do now is simply subtract 180 degrees for that. And if we subtract 180, we'll find that when we have a mean longitude of 21.6, that's what we need. Now if we go up here to T, we'll find our orbit time, which is 7,069 seconds. And we are just about 180 degrees off. So if I do a quick, this is going to be a divide by 2. We'll 7069 divided by 2 is just about 1 hour from now, minus about 30 seconds. So we're going to be making our, coming up here to the upper right where the clock is, we're going to be making our trans-Earth injection. It looks like it's about 1818. Right now my my overlay is blocking that. I think it says 1818. There's got to be a different way to get UTC on here. Well, the other ships have mission clocks. This one does not, which really ticks me off. So there's no way to actually tell time on this ship. But anyway, so we are going till true longitude is 21.6, just about 1 hour from now. But before we burn, we need to figure out the budget equations. So what we need to do now is flip our R1 and A1, or yeah. So if we take our A1 from F66 and paste that down into F69, we'll get 0, but we have a semi-major axis of 1838, 000, and a circular orbit. So we get negative 816 meters per second. That's okay that it's negative. The main engine thrust will not change, which means we're going to go for F73, our spacecraft mass, which we're going to need to get from, if we go up here to info, and we are total mass 25,362 into F73. Okay. And so what we find is the time to burn is just about exactly 816 seconds. So approximately, not exactly, our burn is going to be about, what did I say? Writing into B68, 18, I think I said that was, I don't know what that was, 1818. So our UTC time will be about 19, oh the heck with it, we'll go 5 minutes back. 19:15:00. That's the time we're going to come back after pausing. $19:15. Just about time to do our burn. So we're going to check and make sure, yes, we are in normal time. We're going to turn prograde. And if you look, here is the retrograde velocity vector of the Earth, of our orbit around the Earth. Okay, so let's flip over to the Earth. And you can see our speed is getting lower. We're getting closer to apogee. And what we're going to be doing is collapsing that. So, real quick, I just learned this. Why are we actually opposite our prograde velocity vector, or our retrograde velocity vector of the Earth? Here's how. So it turns out that we're orbiting the moon at, if I go back here, we're orbiting the moon at about 1,600 meters per second, but we're orbiting the Earth at about 950. So what's actually happening is we're going so fast that when we orbit the other direction around the moon, we're actually in a retrograde Earth orbit. So now if you say to yourself, well, when we escape then we're going to be coming backwards around the Earth, and I thought that's bad because backward retrograde orbits around the Earth is not a good idea. Yes, that's true. But listen to this. When you leave the moon behind, its gravity will begin slowing you down. The moon is moving prograde around the Earth, and so what will actually happen is the moon will slow you down so much that you will actually be pulled prograde again by the time it lets go of you. Now, when it lets go of you, you should be going very slow around the Earth, and that's what pulls you in. Okay. We're almost there. We're at about 1918. And I'm just waiting for our... It looks like I may have missed my opportunity for it by a little bit. So... I actually don't like this because I explained this too long. So we're going to wait one more orbit. It's not going to hurt anything. So we will come back just about 2 hours from here, and I'm going to pay attention this time. Okay, so this is what you're looking for. The yaw tape, when it moves around, you'll get right around 0. That's when your speed bottoms out. And you see now the perigee is swinging around. This is it. This is as low to the Earth as we can get. It's pretty much time to leave orbit now. So we don't have any way of monitoring the amount of delta V. So you have to write this down, right? We're going to do 816 meters per second delta V. Our current speed is going to be 1010 at ignition plus 815. Cutoff is 1825. Here we go. And now I'm going to switch back to referencing the moon because we did our job. Another way that you can also manage that is keep track of your ignition time, and your ignition time will tell you when to begin burning. Oh shoot, I wrote down the orbit of the Earth, not the orbit of the moon. So you know what? We actually need to reference Earth so that I can keep track. It should be about 1825. $1,700. Almost there. 18, 10, 20, 25. Okay. So don't let the orbit of the Earth scare you. That's okay. Remember what I said. Moon is going to pull us in and slow us down. That won't happen. So you do not need to worry about the fact that the orbit around the Earth looks scary. It will eventually evolve into what we want it to. So I'm releasing prograde, and let's turn us back to the moon for a nice view of departure. It is a new Earth, which means it's a full moon. So another thing too that could help you is if you pull up the map, if you want to get a better idea of where you should burn. You're going to burn at longitude of 180 degrees because the moon doesn't rotate with respect to the Earth. So in the single case of the moon, it is actually really helpful to know that your burn is going to take place over the anti-meridian of the moon, which is exactly opposite of the center of the Earth. This only works in the moon, specifically because the moon has the singular case of rotating at the same speed that it orbits. And now you can see our orbit around the Earth is starting to look healthier. Being this high up, we don't need any lights. I'm going to turn those off. Okay, so now if you look, that periapsis altitude is counting down, and the Earth is getting stronger gravitationally. The moon is getting weaker. So the moon has now slowed us down, and it's letting us go. So now we're going to be turned back over to the Earth. Okay, so if you notice, our periapsis altitude of the Earth has now gone negative. So we've actually done this burn too well. We're going to need a mid-course correction maneuver to prevent ourselves from burning up into the Earth's atmosphere. And now you can see we've got our new moon, or our full moon. So guess what? We should see a dark Earth behind us. And the sun, of course. And there it is, right there. Perfect. So see what I mean? Much easier. You don't have to really rely on complex math to get back to the Earth. We're just about done with the moon now. There's basically nothing going on there. That's pretty much it. So now we're just coasting back to the Earth. And when we get further away from the moon, when the moon gets less than 1% of its gravity, or 1% of our gravity, that is, then it won't perturb us, and it will be time for a adjustment burn before our altitude gets too low. And you know what I just realized? Right here, we're also at our node. I wanted to mention that. I didn't even think about the possibility that it could be this far out. So let's see. Have we passed the node? TN. I guess the time to node is not listed here. So what we're going to do now is go to align planes. And we don't want to reference the sun. We're going to have to reference the Earth like that. We could target the ISS, because why not? Okay. Actually, let's see. Is it possible to target? Yes, there we go. Okay. Okay, so we're actually right at the descending node right now. And what we want to do is try and land back at Cape Canaveral. So this goes back to the inclination thing. By the way, note how when we were at the moon, we didn't have any westward shift of our orbit more than like half a degree. So you can see why inclination is so key to getting right on the moon if you want to land where you target. So what we're going to do is we're going to target Earth, and we're going to change this by going to display orbit plane. And now we're going to find that it's not displaying because we're too far out. So we can do it another way. We change the frame to equator and projection to ship, and we find that we have an inclination of 55 degrees. And that was reminiscent of the fact that we went out in a negative direction on the moon. It's not the same as when we went in, because we rode the moon around the Earth and through its plane a little bit. So it's a little bit different. 55 degrees of inclination is plenty if you want to be able to catch Cape Canaveral. In fact, it's pretty close to the ISS. So we actually don't need to do a plane change here. That would kind of be useless. But what we do need to do is perform a saving burn to prevent ourselves from burning up into the atmosphere. So what we'll do now is perform a little bit of outward at 90 degrees out. Right here. Right, and this little bit of outward burn is going to prevent us from smacking into the surface. So we're going to do a new maneuver, which is very exciting and somewhat dangerous, that you have to get right, called an aero capture. Well, technically it's aerobraking because we're captured. We're not doing a reentry. if you want to see a reentry, you can see my reentry video. But what I am doing is a aerobraking, which is going to slow us down to the point where we have a circular orbit. The key is leaving the atmosphere, which does not have a defined boundary. It's just a very slow kind of to nothingness, precisely when you have a circular orbit. So we have to target an altitude. We're not going to get this low, but we're going to target 30 kilometers in altitude. So let's go ahead and turn this on and begin rising through the mantle until we get to 30 kilometers. We'll have to do another alignment burn, but it's very simple. I overshot.
Attitude off.
Not paying attention. Let's add some negative translation here. That's take too long. Let's just open the retro doors and do it this way.
Nose cone open.
We'll have to remember to turn those off when we re-enter. So yeah, there's a tremendous waste of fuel. Okay, we're not getting any closer than that.
Nose cone closed.
Alright, let's face our home world. Once I remember that I left
rotation
translation on, and head down towards it. So we'll do one more mid-course correction maneuver when we get a lot lower and can properly select our altitude when it won't be perturbed by the sun. As you can see, the altitude's already 170. That's fine. Orbit's not very accurate when the Earth is only accounting for 40% of the interactive gravity. That might be viewed as an accuracy meter. It's only like 40. That altitude is only 42% accurate. And if you get good enough with your orbit predicts and you have some crazy math and start involving calculus, you can actually predict where the curves are, and then you can burn so that as soon as the turnaround occurs, in changing altitudes, you'll be right where you want to be. Okay. So now we've got our orbit track, and as you can see, it's just about exactly what we said. You know, it's 53 degrees. That's plenty high enough to get to anything, including Russia. So checking our altitude, we're below 234, so we're about halfway in terms of time back to the Earth, but only about a third of the way in terms of altitude. And as you can see, our orbit plane is rotating over as the Earth rotates underneath of it, hence the westward shift. We're also below the surface of the Earth quite a bit, I mean below the equator, so our latitude really isn't changing because we're pretty much on a straight line trajectory. Okay, about 75% or so for this. We're starting to get pretty close. I'd say we could probably do our final mid-course correction when we're at about 100 megameters. So we're almost there. That's pretty much settled. We're at about 85%. We should be able to get a pretty good predict. We'll have to adjust this one more time, but it should be very minimal. So to decrease altitude on an approach, you burn negative outward or inward, which is 270. And there is no autopilot for this, so this requires manual steering. And you notice we're closer to the Earth now, which means it's going to take more energy to achieve this, but it's going to be all right,
Translation.
just as long as I pay attention to this. Okay.
Rotation.
At least I remember to go back to rotation in time. So that's it. I say that a lot. We're pretty much ready to coast all the way down to the Earth now. I like it. Staying pretty stable around 30 kilometers. So again, we're not going to get that low. What's going to happen is the orbit will cause us to rebound. And when it does, we will lose our speed, and that is how we will re-enter. Which means it's important to add that so that we can keep track of our vertical speed. This isn't the way you do it in a fully realistic craft. Don't do it this way, because it will most likely end in death, because we're below the geosynchronous altitude now, because 30 kilometers is too low for just about everything, but not for this crazy DeltaGlider, because you re-enter by turning left and right in steep banks, exposing your sides to space, but whatever. Okay, so I think we've pretty much nailed periapsis altitude. As long as it's within 1 kilometer, I'm happy. So that's it. There's no more adjustments needed. So watch, our orbital speed is now up to 5 kilometers per second. It's going to be just about where we left it, probably between 10 and 10.5, maybe even above 10.5. And we're getting down there now. Just about 30 seconds at this rate, we'll be at our perigee. And we're not doing a burn here. We could do a burn using the Viz-Viva equation, but I'm going to take advantage of the fact that the Earth has an atmosphere. Now 8 kilometers per second. Okay, we're really starting to get low. 8 million kilometers. I'm only at 10 times the rate, the normal rate. So, our periapsis altitude has slipped up a little bit. And that's the wrong direction, unfortunately. You got to make sure it's low enough, or you will skip. And if you skip, you're done. Well, not in this case, because we're captured. If you're not captured, you're done. It's game over. So I'm going to reinforce this principle now by taking care of it, setting out what I meant to do. That's fine. Okay, let's see. Oh, we're below. Okay. We're actually below 1,000 kilometers, and we go down very, very quickly. So at this time, it's extremely important that we configure for atmospheric flight. So we're going to go to surface. We're going to turn the HUD to red. We're going to turn our lights back on, and we're going to retract the radiator. That is very important. Make sure our retro doors are closed, because we're about to get some serious heating. Again, the goal is to stay in the atmosphere just long enough that you get a circular orbit. Or something close. You're never going to get something perfect. If you get something perfect, you were lucky. You were a hair from falling into the atmosphere. Okay, so we are just about 6 minutes away from the periapsis. And yeah, we're just about at 10.5 kilometers per second. We'll be going a little bit faster than that when we smack into the surface. And yes, we're using a very steep angle. It won't be quite this steep because we're starting to get to the lowest part of our orbit. But yeah, if we, again, don't do this in a fully realistic craft. When I get within about 2 minutes, we're going to activate the horizon level autopilot. This is going to be like a rock skipping off a pond. You'll hear nothing, and then all of a sudden, you know, that you'll hear the atmosphere start roaring within a matter of about 10 seconds because of the steep angle that we're coming in. I mean, you can see we're basically going down about 2.8 kilometers per second. So, yeah, this is the ominous part where from Apollo they show the craft separating from its service module in Apollo 13, and then they're like, the Earth is getting pretty big outside the window. Can you give us a reentry estimate? Because this is real time. The Earth really does get bigger this fast as you come up to it, and you see the clouds, you see the ocean, you see the atmosphere, and then you realize, oh my gosh, here we come. Okay, dynamic pressure is registering on our surface MFD. This is what we're going to watch for static and dynamic pressure. We probably want dynamic pressure somewhere around 25 to 50 kilopascals. Above 150 kilopascals, that would be considered hull rupture. I would try to avoid making it that much because I try and make it as realistic as possible, as long as I'm going to be able to do what I need to. 4 minutes from periapsis. And keep in mind, too, we're coming in at above 10.5 kilometers per second, so we're not going to hit our atmospheric interface at the top of the stratosphere. 60 kilometers is going to be much higher, probably around 90 kilometers, because of the added speed. We're going to have a lot more drag at a much higher altitude. Okay, we're below 235, so at this time we're getting too low. We want to activate the horizon level autopilot to keep us stable, because this is where we want to begin. What we're going to do is we're going to shallow the vertical speed until it almost levels out. And then when it levels out, that's when we're going to perform our bank. Okay, here comes the dynamic pressure. We're going to perform a steep bank, and the bank is going to allow us to fly through the atmosphere. And when it's time to leave the atmosphere, when we have a almost circular orbit, not quite, but almost circular orbit, because we're going to lose more speed as we try and get out, we're going to turn horizontal and pull the stick back, and we're going to fly up and out of the atmosphere. So that's how that's going to work. Okay, I'm going to save. We should be getting atmospheric interface within just a few seconds. So this is where, you know, in the case of the Apollo astronauts, everyone would be buckling in and being like, okay, are we going to still be here in 5 minutes? We're only performing about 2/3 of the first of the skipped reentry of Apollo. Apollo did 2 reentries. It did an initial one to bring the orbit suborbital, and then a second to kill off the majority of the remaining speed. The second was the scary one. at least for the astronauts. Okay, here we go. All right, I'm ready to grab the stick. Okay, decelerating. Actually, not quite yet. Okay, now we're decelerating. Listen to that. Okay, we've actually lost attitude control right now for a temporary amount of time. We can't prevent us from losing altitude. And yeah, you hear that? That is atmospheric reentry at 10.5 kilometers per second. Okay, disabling, and we're going to turn sideways now. Wow, I'm going to need air flight control surfaces because I don't have enough control here. And what we're going to do is we're just going to keep this relatively low. We are losing speed very... Why is the orbit shrinking? Something's not right here. We're losing altitude, but not speed. Oh, okay. I see what's going on. So we're losing altitude and speed. So we're gaining altitude. I don't want to gain altitude, so I think I already lost. I'm trying to get the ship to come back into the atmosphere before we steer out. Yeah, I think I might have already lost. You really got to be on your game. Yeah, it's going up. We're still bouncing. One thing that I can try doing as a last-ditch effort is to open the aerobrake. And the aerobrake will try and slow us additionally a little bit more. But yeah, we're bouncing out of the atmosphere. We've lost. So we could do a second round and circularize, which I think I will do. We're gonna go back out to about how high are we going? Just over geosync, and we'll have to come around for a second pass. It's really critical that you get it right. Let's see how far. We're not far off periapsis, but we still haven't killed the majority of our speed, so we're going to have to come around for a different cycle. The key is to get right about 45 kilometers. That's your sweet spot. I didn't act when I should have because I noticed the orbit changing, but I didn't pay attention to the speed as we were losing altitude. It's a confusing thing that you don't really understand until you're doing.
Ladder retracted.
Sure.
Door closed.
Okay, I need to download the sound mod update. So quick save, and we're going to redeploy our radiator, but we shouldn't forget about that. And we're going to ride the orbit around and bring our perigee back down to about 30 kilometers when we get back up to apoapsis. So with that, we will note where we were, which is, I actually don't recognize, okay, we're over the Middle East. That is awfully gray down there. It's almost like black and white. Holy cow. Really sandy desert down there. Okay, we're coming back at apogee. Okay, so here we are all the way out here again for apogee. All we're going to do is just lower the altitude back to 30 again, and we'll go back in for a second pass. This time I'm going to be much more mindful when I get into the 40s. Now, in the case with the DeltaGlider 4 and the XR2 Ravenstar, you don't have this kind of issue because you can perform what's called a center of gravity adjustment. And what you do is you actually impact the incoming air head on. So you can totally eliminate the lifting component, and if you eliminate the lifting component, your vertical speed won't slope upwards like it did for us. The problem is we get a lifting component.
Translation.
Look at how slow we're going, by the way. We killed off 90% of our speed. Done. That was it.
Rotation.
Yeah, so the issue is we had our fins exposed, and the fins will generate lift. And they actually generated so much lift that I didn't take control of it while I still could have. And what happens is you slow down, and then you start heading out of the atmosphere. And if that vertical speed gets too high, you just bounce out. So it's pretty hard to get it right in this craft. Okay, anyway, we're going to go back to just a few minutes before re-entry now, just above the Earth. Okay, here we are below 500 kilometers again. So it's the same deal. We're going to retract the radiator. Make sure our retro doors are stowed. Just give the craft a once-over, and once that radiator or nose cone, whatever it's named as, retracts, we'll be good to go. So here we are with all 10 kilometers per second again, ready to try this again. So what I'm going to do differently this time, I've actually never tried this before in the stock DeltaGlider, mainly because I don't like how unrealistic the re-entry is. One thing I will do is release the craft at 60 kilometers instead of 50 kilometers. I waited a little bit too long to release that autopilot. I probably should have released it about 60 kilometers. If I had done that and then steered at 60, we probably would have had a different outcome. But it is a fine line. You know, you go too steep, there comes a point now where you're on a death dive and you can't steer out of it. And that's when you get the meteor effect. Okay, yeah, we're at the right time. Okay. Below 300, when we get back to 240, I'm going to put the autopilot on for horizon level. And mark 240 in 2, 1, now. Ooh, that is a mountain range. It really irritates me that I don't know where this is. I'm really good with my geography, but I'm just not getting it. So we're at 135 east. Oh, okay, so this has got to be Java. Got to be Java or New Guinea. Okay, we're below 180 kilometers now, so we're about to get some serious heating on the way. I just thought about it. I'm not so sure I actually want the horizon level autopilot on. To be honest, I think I have such positive buoyancy caused by the excess lift of the atmosphere due to my high speed that I think I can just come in this way and be okay. Now, I did leave the air flight control surfaces on because we're obviously going to need them. But if we start getting too low, I'm pretty sure just turning right out of this should should give me plenty of capability for getting out of the atmosphere when I need to. Here we go. So what I'm going to watch is the periapsis altitude and prevent that from rising or sinking too far. Okay, here we go. 56, 55, 54. Yeah, this seems much better. Oh yeah, this is the way to do it. There we go. Alright, now we've got a G of deceleration. That's where we want to be at. Okay. Yeah, like I said, there's a fine line between having it and losing it, and now we've got it. We're in control over our vertical speed. Okay, I'm doing between 2.5 and 3 Gs, so I don't want to make it too out of control. Whoa! Okay. What in the world? Okay, it's a wing stress. Apparently I exceeded the wing stress of the craft, which is a little bit concerning. So I have to figure out now how to get myself out of this without purposely or fully destroying the craft. And the only way to do it now is to get out of the atmosphere. So this is it. We have a fully circularized orbit now, and I really need to get this out of the atmosphere now. Okay, we're below 8. Okay, we're fine now. You can relax. Pretty cool, huh? So that's how a reentry works. Now, I'll have to review the footage to see why it thinks that the wing stress was exceeded. Wait a minute. Did I leave my air brake out? Oh, I think I exceeded the control surfaces. Okay. Well, somehow I managed to fly us out of the atmosphere without an elevator or an aileron. So I'm going to call that in and of itself a masterpiece. So I know this is a disaster, but that's okay. Again, I'm really not a fan of this DeltaGlider, and to be honest, our next tutorial is the last one with it. I've done aero captures around Jupiter successfully before in an XR, that takes a mad amount of concentration and skill, because you are going 60 kilometers per second, and the difference between burning up and skipping off of Jupiter and leaving the solar system forever is so small. It is so very small. But I've done it, so that's it. We've actually killed off. You can see we're down to 8,200, so we've only got about 800 meters per second left to kill. And look at the total amount of fuel we've burned. Not that much. So if you wanted to do it the other way, that was guaranteed to end in a success, then you can turn retrograde and do the vis-viva equation for the incoming orbit that we had. It's a semi-major axis, and then a semi-major axis that is your altitude, and that will give you a delta V. and then you figure out your mass again with the engines to get the time. You need to do the burn. You start the burn half of that time in front of you hitting periapsis. You burn until you're circular, and once you're circular, you can use my reentry video. So thank you guys for joining me on this destructive adventure, and I will see you guys next time, where we introduce a new tool, and we're going to fly to Mars. And that's where I am going to stop using this craft because it's kind of bugging me. It's just a mess. Start looking up TransX. That's what we're going to be focusing on. Get that downloaded if you're watching. Get that ready. I don't know if TransX comes standard with Orbiter now. It used to not. I think now it might. So start looking up TransX. TransX is your key to flying the solar system. This has been Dr. Aeronautics, and I will see you guys next time. Bye-bye.